Morning, can you all hear me?
Yeah.
Okay, so why don't we get started? So these next few weeks are going to be kind of busy for you folks, and probably for me too, because I'm going to be grading a bunch of labs. Anyway, you have an exam coming on the 19th, it's Unit 4. The DC Circuits lab is due on Friday. Remember, from now on, for lab, you're coming here. Okay, so, and then the scope quiz is due on the 10th. So I sent you all an email regarding the scope quiz. We should have the video for the oscilloscope quiz. Tyler was making it yesterday. We should have it out soon, maybe either today or tomorrow. And what you're going to be doing for the scope quiz is basically you're going to be demonstrating that you know how to use this device. This is an oscilloscope. And it's used to measure voltage as a function of time, and it's probably the most important instrument an engineer will use. It's more important than the multimeter. On Friday, I will talk a little bit about this device. You should also watch the video, which should come out shortly. This equipment will be set up tomorrow. So you can come to the lab starting tomorrow and play with this equipment. If you're get comfortable on it by Friday, then on Friday, Tyler and I can test you on this device. If you look at page 6 of the lab, there's just a series of, I don't know, 6 or 7 simple steps where you have to just demonstrate that you know how to make a measurement with this device. So what will happen is we'll have a signal generator, which is a device that we use to generate a time-varying voltage, a signal. And you're going to measure the voltage and the period of the signal with this oscilloscope. Basically, you're going to be demonstrating to us that you know how to use it. It's actually not that hard to use. There's a couple little tricky things, but those things, you'll learn later. Okay, so we want you to get started on learning how to use this because the subsequent labs are going to require you to use the scope. Okay, so all you have to do is ask for us to test you. We'll watch you go through the steps, and if you've completed it, then you get a 20 out of 20. We'll sign that last page of your lab. You will turn it in, and you're done. You get a 20 out of 20 on the lab. Okay, that's one of the easiest lab reports you'll do this semester. But you need to get it done by the 10th, which is next Wednesday. The following day is a holiday. The 11th is a holiday, so I'm not going to be around. I'm not even going to have office hours that day. And then on the 12th, I'm going to introduce to you the next lab, which is called the RC, which is called a Transient Lab. And that's a lab where you're going to use this equipment and make measurements with this equipment. Okay? So we kind of need to get you to know how to use this right away. Like I said, just measuring voltage as a function of time with this is not that hard. Okay? So please try to get this done fast. Don't wait. Don't wait, because I know a lot of you guys waited to do the Ohm's Law lab and then struggled, because I gave you guys a month to do it, and then you struggled. This you should be able to learn quickly, and you should get out of the way quickly, so you can do the next lab. Okay? It won't take very long. In fact, you can probably listen to my lecture on Friday and then get the test, the quiz done that same day if you have some time to practice with it. Okay, that's how straightforward it is. Okay, but I want you to get it done right away. I'm hoping you can, especially this group, can get it done on Friday. You can come in early on Friday. I know our lab is at 2 o'clock on Friday. You can come in early because you'll have a chance to watch Tyler's video. And you can play around with these devices. Okay? And if there's more students in the lab, we'll put more scopes. So we have a lot of scopes. So we can put as many as we need to for students to practice on. Okay. Questions on that? Or concerns? One of the goals in this course is to try to get you comfortable with using fancy equipment. Okay, that's important, especially if you're going to be an engineer. All right, the exam 3 average was 76%, which is actually quite good. Okay, that's actually a pretty good average. And I'll be honest, the average is going to really fluctuate with this group because there's only 6 of you left. Okay, in this group. And so, you know, it just, nobody got below 50% on this exam, which made me very happy. Okay. Whereas the other group, half the class, got below 60%. Okay, and maybe a third got below 50%. But this group, nobody got below 50%. Actually, nobody got below 55%, which made me very happy. I could be wrong, but I think nobody got below 55%. But so that's, I mean, and that's kind of what I expected for this exam. I expect usually on average between 70-75% on this exam, although it doesn't always happen. So I was happy with that. So today, what I want to do, we have a lot to cover. We're going to talk a little bit more about charged particles and magnetic fields. We're going to talk about the force on a wire in a magnetic field, the torque on the wire in a magnetic field, and the DC motor. I actually have a DC motor, a big one, so I can put it right by the camera so you can actually look at it, okay? So you can do the DC motor lab. By the way, starting on the 15th, we're going to have, I think it was the 15th, or the, not next week, but the following, not this Monday, but the following Monday. I think it's the 15th. We're going to have testing equipment for your DC motor lab. And again, don't wait till the last minute. The DC motor lab is due December 3rd. Don't wait till the last minute to build it right away. And then you can come here and test it. So starting on the 15th, we'll have equipment for you to test your DC motor. And once you get it running under 3 volts or less, that's it, you're done. Okay? You just gotta answer 5 questions after that. Okay. And then the last thing we'll do is we're going to start chapter 30 and talk about the Biot-Savart law. So last time, the main equation we really discussed, other than we talked about the properties of magnetic fields, was that if you have a charged particle in a magnetic field, the force on it is equal to Q times V cross B. This involves a cross product. And so you do have to remember how to do the cross product. And in a lot of cases, if these two are perpendicular to each other, you can use the right-hand rule. In order for the force to be non-zero, V has to have a component of its velocity perpendicular to B. And I demonstrated that with the little tube with the beam of electrons going through it. It's called a Crookes tube. Okay. And we also talked about the properties of magnetic fields last time. We talked about the fact that really a magnetic field is an electric field viewed in another frame. And I'm going to send you a document, since you guys have already covered relativity. I created a document that kind of illustrates that. I have a little 3-page document that I wrote up that shows you the relationship between, or indicates to you the relationship between the electric and magnetic field. Okay. It's basically the example I talked about the other day, but I worked it all out. All right. There's only 3 pages. It's not very long. And I don't think the discussion is very difficult either, because you've covered all the material. Okay. So we say, well, what if we have a charged particle in a magnetic field where V and B are perpendicular to each other? Well, remember that from the cross product, the magnitude of this force is Q, the magnitude of Q, times the magnitude of the V. And I'm going to write the V as a script V. I know I didn't do that last week, but today I'm going to write some equations with voltage in them. And so just to discern the two, I'm going to use a script V for a velocity. The magnitude of the magnetic field, and then times the sine of the angle between these two vectors. And then when we talk about the angle between two vectors, we put the vectors together tail to tail, and this is the angle I'm talking about. Okay? That's what that angle is. It's the angle between these two vectors when I put the vectors tail to tail. Okay? Now, if sine of theta equals 1, in other words, theta is 90, then we have the magnitude of the force is Q V B, where all these are magnitude. If I drop the scripts from this, I can write it like in the following way, indicating that these are just magnitudes. And since the force vector is always perpendicular to V and B, the force will be perpendicular to the velocity vector. This is going to produce circular motion. You're going to have a centripetal acceleration. Just imagine, again, tying a rock to a string and whirling around in a circle. The tension in the string is always perpendicular to the velocity vector. And so this force does no work on a charged particle. This force does not change the kinetic energy of a charged particle. That's what that means. Okay, is that clear? If the force does no work on a charged particle, that means that it doesn't change the kinetic energy. All it does is change the direction. And so V stays the same. And so if we solve this for R, we did this the other day, we have this equation, mv is the momentum. So you can use a magnetic field to select the momentum per unit charge of a particle. If you know that the velocity of all the if you know the velocity of the particles, let's say you have a bunch of particles coming into a magnetic field with the same velocity, then you can actually select the mass per unit charge of the particle. Or you can actually select the mass of the particle if you know what Q is. Okay. And this is the basis of the mass spectrometer, and I'm going to say a little bit more about that a little bit later today. Okay. Any questions about this? A lot of chapter 29 homework is based on, understanding this particular equation. Okay, and the applications of it, because there's a lot of applications of it. Okay. So, given this, I want to ask the following example. I want to ask you the following question. It's kind of a conceptual question. From the drawing shown, I want you to rank the speed of the charged particles from fastest to slowest. Assume that the mass and magnitudes of the charges are the same. And assume that the magnetic field points into the plane of the page, or into the board, or into the screen, okay? Which object, you guys tell me, which object has the greatest velocity? Which one's the fastest?
I would think A.
So you think it's A?
Yeah.
So let's take a look. So this is
Ryan says C.
I'm sorry?
Ryan said C.
Ryan said C? Or Ryan, I'm sorry. So why choose? Why did you choose your choice? Why did you make your choice? Like, give me the rationale for your choice.
I mean, mine was just that it takes less time for it to go. I guess that's a time-based thing, but just that it's a closer, a smaller radius. That was my reasoning. But
Mine was actually because it has a bigger radius.
Yeah, if you look at this equation, right? R is equal to mv over qb. The bigger R is, the bigger V is. Isn't that true?
oh yeah,
And they all have the same mass, and they're all in the same
Yeah.
field. And so
Same
if this
charge.
is bigger, V has to be bigger. So it has to be C. Now the next question, and this is a harder question, what is the sign of the charge on those particles? We can actually determine the sign of the charge on those particles. Okay. What do you think?
I can't tell what they are, but I can tell C and A are the same,
Good.
and B will be different.
Okay, that's good.
yeah. I was trying to think that because B is going in like it says that the magnetic field points into the page, so that means B is going opposite direction.
B is going opposite of A. So we know that, I mean, we can tell that A and C have the same sign and B has the opposite sign. So if I can figure one of them out, I'm done, right?
Yeah.
So before I answer the question, which way should the centripetal force point?
Radially inward.
Okay, it has to be radially inward. Okay, so let's remember that. Let me draw this magnetic field better. I'll draw it here. So the velocity is this way. So let me draw the velocity vector here. Okay, and let me draw the magnetic field vector into the board. So B is into the board, which is hard to draw. If I used my right-hand rule, right? Let me draw it better. If I use the right-hand rule, which way does the force point? Point your fingers in the direction of V. Curl them towards the magnetic field. The magnetic field's into the board. So I got to curl them into the board. My thumb.
So it's radially outward.
So it's radially outward.
So then the charge is negative on A and C.
Yes.
Okay.
Okay. Because we know that the force has to be inward, and we applied the right-hand rule to a positively charged particle, and it gave us the wrong answer. That means that this is a negatively charged particle. Okay, you can apply this to any part of its motion, right? I chose an easy point. You don't want to choose a point over here, right? You can choose this one too. This one would give you the answer here. So I would choose any one of those points. If you did B, it would work. If you did B, the force would point towards the center of the circle, and then you know
Professor?
that B is positive.
Can you explain the right-hand rule one more time? I think Jacob was asking about it in the chat.
Oh, I'm sorry.
Oh, it's okay. I cut you off, kind of.
So you point your fingers in the direction of V, okay? And then you got to curl them. You need to curl them towards the magnetic field. So you got to curl them into the board because the magnetic field points into the board. Okay? So I curl my fingers into the board and my thumb points in the direction of the force.
So Jacob, it's kind of hard to see. I don't know if you understood, but the force is going straight down. It's being cut off by the screen a little bit. So
Oh,
your
oh,
hand
okay.
points straight down, and then you curve your fingers. B is pointing straight back, but he can't draw it that way. So you curl your fingers into the board that way, and then your thumb points towards the force.
Yeah, let me try to do it this way.
Yeah, so your fingers are pointing straight down towards the velocity. Yeah.
Yeah.
And then you curl your fingers where
Tor-
B is, which is straight into the board.
Yeah, so
he's
this would
drawing
be
it at an
B.
angle.
Does that help or not? If I do this.
So your palm faces the magnetic field. It points towards the magnetic field.
Yeah, my palm, could I have to curl my fingers towards the magnetic field? Right? I have to curl them towards I have to curl my fingers towards it's hard to do this, to the purple marker, like that.
Okay.
And so F points that way. There's other ways to do it. You can do the following with just your 3 fingers. So if you point, forgot how this one works.
Is your pointer finger down?
Yeah, your pointer finger's down, your middle finger's in the direction of the magnetic field, and your thumb points in the direction of F. So you can do it this way too. This is the direction of V, this is the direction of B, this will be the direction of F. Okay, so you can do it that way too. Because then you can use these fingers then to define a right-handed coordinate system. So direction of V, direction of B, direction of F. So that's another way to use the right-hand rule. Some books do it that way because some students have a hard time with, it's basically how a screwdriver works, right? You curl V into the board. You're basically curling this vector into B, and your thumb will point that way. It took me a while to learn it too, so I hope that helps. And I know this got cut off a little bit, sorry. Yeah, the palm faces the magnetic field. And then you curl your fingers towards that magnetic field vector. Okay?
Okay, thank you.
Sure. Yeah, so it's called a right-hand screw rule. That's what a lot of people, they don't call it like that anymore, I don't think. You don't see that in the books anymore. But that's one way to learn it, and the other way is to use your 3 fingers. Your index finger's V, your middle finger's B, and then your thumb points in the direction of F. Okay, so A and C are negative, B is positive in this one. Okay. So, applications.
Wait, Professor.
Yeah.
Why does that make A negative? Just because B is pointing into the board, or?
Well, we said that the force points this way, right?
Yeah.
What's the direction of centripetal force on this thing?
Isn't it?
It's
centripetal force is inwards. Right?
It's inwards, right? That doesn't agree
Yeah.
with that, right?
Yeah. Okay, that makes sense.
Yeah, because that applies to a positively charged particles.
Yeah.
So
okay.
that means this has to be negatively charged.
Okay.
So let me just give you an example of this. Actually, a couple of examples in nature. One of them is the Van Allen belt, which were discovered, I think, 1958. Now, any planet or any celestial body that has a magnetic field will have such belts. And these are very high energy charged particles that are trapped by the Earth's magnetic field. These charged particles will come from the solar wind. And these are particles that come from the upper atmosphere of the sun. Okay, and they could be, most of them are protons, electrons, and helium ions, alpha particles. And as they move from the sun towards us, and these are very high energy particles. We're talking about, for the protons, we're talking about MeV particles. The Earth's magnetic field traps them, which is important because highly charged particles, if they reach our atmosphere, they're going to slow down. And when they slow down, they give off radiation. And that radiation would not be good for us. Okay, I mean, if you can actually get a Geiger counter, measure, just count, just look at the counts when you're on the ground, and then look at the counts when you're on an airplane, and you'll see you're picking up more counts in an airplane. Because the further up you go in the atmosphere, the more charged particles you're going to be interacting with. Okay. Well, these belts are where the charged particles get trapped. Let me make this picture bigger. And there's two belts. There's an inner belt and an outer belt. The inner belt is from about 1,000 kilometers to about 12,000 kilometers in range above the surface of the Earth. And they contain high energy protons. They're like above 50 MeV, mega electron volts. And some electrons that are around 100,000 electron volts. And they're trapped within. So that purplish region you see, that's the consists of protons and some electrons. The blue range, which is further out, from about 8,000 miles above the Earth to about 37,000 miles above the Earth, in that range, they consist of mainly high energy electrons from like 0.1 to about, let me look this up, 10 mega electron volts. And they're mostly electrons. And they're trapped by the Earth. Now, and when they're trapped by the Earth, you can see in the bottom figure, the particles actually exhibit a spiral trajectory as opposed to a circular motion. And that's because, one, you have a non-uniform magnetic field, and two, the velocity vector of these particles have a component parallel to the magnetic field and one perpendicular to the magnetic field. I think the motion is kind of complicated because, one, you have a non-uniform field to the Earth. It's like a bar magnet. And two, the velocity vector of these particles have components parallel and perpendicular to the magnetic field. Now, some of these particles will actually will actually enter our atmosphere high up above the Earth. And a lot of times what they'll do is they'll enter the atmosphere near the poles. And the reason why they'll enter there near the poles is because the force on them is essentially zero, because the direction of the magnetic field and the direction of the velocity vector, they're essentially parallel to each other. These particles then interact with the gases in the atmosphere, like nitrogen, mainly nitrogen. And it excites it ionizes and excites the atoms, molecules in the atmosphere. Like in that tube I showed you the other day. The electrons get excited into a higher level state. Then they get de-excited. For example, it's the difference between taking a ball, putting it on top of a hill. That's an unsteady state. The ball will want to roll down the hill. So when the ball rolls down the hill, its potential energy gets converted to kinetic energy. Well, same thing with the electron in an atom or a molecule. When it goes into a higher energy state, it's in an unstable state. It gives off its energy in the form of light. And so in the case of nitrogen and other atoms, the light is kind of a bluish-greenish color. And they form the northern lights. And of course, they're also in the south, near the South Pole. Those are called the southern lights. Questions on this? So the magnetic field really, the magnetic field of the Earth protects us from these charged particles, which is important. Otherwise, we'd have much higher cancer rates. So let me give you another example of the applications of these ideas. Most books call this the velocity selector. So I want to give you an example of something called the velocity selector. The people who are in accelerator physics, they'll call it the Wien filter because it was Wien, German, who designed this. And Wien was one of the first people who started to develop the mass spectrometer. I don't know if you folks have had chemistry yet and talked about the mass spectrometer in chemistry. Let's say we have a set of plates. Okay? And I have a beam of positively charged particles moving to the right. Let's make the top plate positive. This is a horizontal plate. It doesn't look horizontal. And let's make the bottom plate negative. And so the electric field points downward. And if the particle goes through that field, what's going to happen to it? What happens to the particle when it goes through the set of plates? In a uniform electric field. Well, if the electric field points downward, the force will point downward. And so the particle is going to do this, going to go down. It's no different than if I took this marker and I threw it across the room. It's going to exhibit projectile motion. Okay? So it's going to deflect downward. It's moving through a region of a uniform field, just like the case where I take a ball and I throw it across the room. Well, what happens if I introduce a magnetic field into the board and I adjust the magnetic field? So let's put a magnetic field into the board and let's make it uniform. Well, if I have a charged particle in an electric and magnetic field, the total force on it is going to be given by the full Lorentz equation. And what is the direction of the force due to the magnetic field in this particular case? Well, if V is to the right and the magnetic field's into the board, I use the right-hand rule. Point my fingers in the direction of V, curl them towards the magnetic field, my thumb points upward. Again, I'm facing my palm towards B and curling my fingers towards it. My thumb points upward. So the force out is upward. So the magnetic force is upward. So these are in opposite directions. So if I write this in terms of components, and I can write this without the sine term because I know sine of 90 is 1. Then these two want to cancel each other out. In fact, I can adjust my value for the magnetic field so that the total force is 0. Which means I have to have this equal to that. And so E is equal to V times B. So I can adjust B so that there's no force on the particle. So what does that mean that there's no force on the particle? This particle will go straight through. So I can adjust B so that the particle goes straight through without deflection. So that V is equal to the ratio of E over B. The magnitude of electric field divided by the magnitude of the magnetic field. This device is a velocity selector, meaning that only particles that match this ratio will go straight through undeflected. All the other particles will bend towards one of the plates. Now, how do I keep, now these other particles that go through here will hit the plate and then bounce off. How do I keep those other particles from getting through from this side to this side? Well, what I do is I put a set of slits here, or an aperture. I make it small enough so that only particles going straight make it all the way through. So these are slits or apertures. And so this is a velocity selector. It only allows particles of a certain velocity to come through. So you can actually design something that only picks particles of a certain velocity. And these are used in mass spectrometers. They're used in really anything, any device that's used to sense ions. Okay. Questions on this? So you can work in a fancy lab with all kind of complicated equipment, but the operating principle is pretty simple. The hard part is making the field very uniform, and that's where the construction details come in, making the fields uniform. Okay, but the principle of the idea is pretty straightforward. One of the things about working in a lab, especially in an atomic physics lab, which I used to do, is what was amazed about it is that most of the equipment you use, you can understand using first the physics you learn in your first courses. Okay. The details of making the fields uniform and stuff, then you need more of the upper division work. But the basics you can as long as you understand the basics, you can understand a lot of the equipment that's in a research lab. Questions on this? So you should understand how this works. There's one or two homework problems on the velocity selector. And again, it's an application of the Lorentz force law. Okay. So how is this used? Well, Thomson used it to measure the charge to mass ratio of the electron. So let me make this picture bigger for you guys. What did Thomson do? He had this tube many, many years ago, over 120 years ago. Whoops. He actually used a velocity selector to measure the velocity of the electrons and then measure the charge to mass ratio of the electrons. So this was his tube. You have the beam going to the right. And so what you see there with the cathode and the anode, that forms something called an electron gun. It's a source of an electron beam. The old TVs that use a TV tube, the color TVs had 3 of them, had electron guns in them. They produced a beam of electrons. The beam of electrons was shot to the screen. And when the beam hit the screen, it was phosphorescent. It would glow. The oscilloscope that you're going to be using also has an electron gun in it. that screen that you see that I'm covering with my hand, the screen that you see is phosphorescent. So when the electron beam hits that screen, it glows. Okay, so this thing that you're going to learn how to use has an electron gun and tube in it. Basically the same thing as you see in the Thomson experiment. So what Thomson did was he needed to measure the energy, the velocity of the electrons. When you have an accelerator, it's actually very hard to actually measure the velocity of electrons because you have all kinds of stuff coming out, and because the holes or the apertures where the beams come out, they give you a spread of energy of particles. You want to have a good way to measure the velocity of the particles. So what he would do then is he would send a beam through a pair of deflection plates. And he would apply a voltage across those plates. And of course, the voltage potential difference between those plates divided by how far apart they are gives you the electric field. So he knew the electric field. Then perpendicular to the electric field, as we showed in this picture here, as we did here, he applied a magnetic field. He adjusted the magnetic field until the electron beam went straight through and made a dot at the center of the screen. At that point then, once he knew E and B, then he could calculate the velocity. Then he would turn off the magnetic field and then watch the beam of electrons deflect. And using kinematics, I mean real basic kinematics, you can calculate that deflection. Okay, because once the electrons are in the plates, they're being affected by a uniform field, like when you throw an object across the room. Once they leave the plates, they're in a field-free region. They keep going in a straight line. And so you can use that idea to calculate delta Y. It's really not that hard. I mean, you're using physics 205 ideas. And so all you got to do is measure delta Y. If you know the geometry of the plates, you know how long the plates are, and you know the distance from the end of the plates to the screen, you can easily calculate, derive an expression for delta Y. I'll show it to you in a minute. For delta Y in terms of the geometry of your plates. And that expression that you see, I'll make this big again. That expression that you see looks complicated, but both terms have a Q over M, which is the charge to mass ratio of the electrons. You can pull that out, and then everything you have in the brackets are quantities you've measured. So let me do that on the board. If you take that equation and you pull the Q over M out, everything that I'm going to have in the brackets is measurable. 1/2 E times x1 So all this stuff is measured already. And this is measured, so you can get the charge to mass ratio. And he was able to get 1.76 times 10 to the 10th coulombs per kilogram. Millikan later was able to actually measure the charge of the electron and showed that charge is discrete. Now, I know it says in that slide, complete the derivation. You don't have to complete the derivation. However, you should try to derive that. That's good practice for you folks. You should try to derive that equation. Okay? That's really good practice. So if you want an extra practice problem, you should try that. That will help you understand the material from Unit 2 better. Okay? I highly recommend that you try doing that problem. Oops, I had this wrong. This is to the 11th power. Okay. There's a lot of interesting applications of these ideas. One can spend a long time going through them, but don't have time. Suppose I have an accelerator or an electron gun. Okay? Basically, it's a device that sends a charged particle through a potential difference. So this is a little bit of a review of Unit 2. So let's say we want to accelerate a positively charged particle. Okay? This is the cathode, this is the anode. I'm going to put this at V0 and at 0. This is at V0 volts, this is at 0. It's going to go from higher to lower potential. That's going to accelerate the charged particle. And we can calculate how fast this thing is from conservation of energy. Okay. This is going to be Q delta V. This initial velocity is essentially 0. It's not exactly 0, but it's essentially 0. Okay. So that Q delta V plus 1/2 mv final squared equals 0. So minus Q delta V is 1/2 mv final squared. Well, what's delta V? Delta V here is the final potential
Hey,
minus
Professor?
the initial. Yeah.
I don't know if it's the same for everybody else, but the accelerator's getting a little cut off in the picture.
Oh, it is. You're right. Sorry. I wonder what happened.
No worries.
Let me fix the camera. Sorry, I'm too close to the camera.
No worries. That's perfect.
Okay, let me, yeah, now we can see the whole thing. Is it blurry or is it okay?
A little bit blurry on the left.
Okay, that's what I see too. Okay, I'll try to use a dark marker. I hope this is dark enough.
I can see all the equations fine, but the accelerator is just a tad blurry.
Is that better?
Yeah.
Okay. So delta V is the final potential minus the initial potential, which is minus V0. So minus and a minus give you a plus. So V final is the square root of 2Q V0 over M. So let's assume then that these particles now, well, not this assume, this is the velocity of the particle. So let me redraw this, because I wrote a bunch of equations. So the particle comes out like this. And we can have a velocity selector if we want here. Okay, that's fine. But now I'm going to send it into a magnetic field. And when I do that, the particle is going to go straight through, and the magnetic field is going to bend it into a circle. We're going to choose a magnetic field that's such that its direction is perpendicular to the velocity vector. So I can bend the particle into a circular path. And when it goes into the magnetic field, this particle is going to go in a circle of some radius. And then I have a detector here to detect the particles. Okay? This is a mass spectrometer. Have you talked about mass spectrometers in chemistry?
Yeah. They're the things that you see light with, right? The different colors of the spectrum.
No, that's not a mass spectrometer. That's just looking at light. Right?
Oh.
A mass spectrometer is used to measure mass of ions. You're talking about a spectroscope, right?
Oh, yeah, I think so.
Yeah.
I think I have used this mass spectrometer because I've heard of it, but I don't remember specifically using it.
Yeah, you talk about these in chem and especially in OChem. Some students who are in this class have had OChem or are in OChem. And so this is really the basic principles of the mass spectrometer. So how do we calculate the radius of this? Well, if we know the velocity of the particle, I'm just going to call this V now. Okay, and I should call it script V because there's too many V's here. Sorry. If I send this into the magnetic field, I know that if B and V are perpendicular to each other, the force on it due to the magnetic field is given by this equation. And this produces centripetal acceleration. I get QB equals mvr, and R is mv or QB. But my V is given by that expression. So R, I'm going to get rid of the slide for a minute because it's getting in the way. Okay. So R is going to be M over QB times that thing. And I can simplify that. I'm going to put everything under the radical. Solve for M. And that means I have to square both sides and solve for M. So I'm going to get Q B squared R squared over 2V naught. So basically, as long as I place my detector in the right place, in a certain place, I can get a value of M. So for a given value of M, for a given value of R, I have a unique M. And so I can put a detector there, and they're very, nowadays, they're very position sensitive. Okay, you can put a detector there that's very position sensitive. And so based on the radius of the path of the particle, you can easily calculate the mass of the particle. And folks in chemistry do that. If they want to measure the mass of a particle, what they do is they ionize it and then accelerate it and measure its mass. Of course, its mass then is going to be, the value that you're going to get here is low by the mass of the electron because you've stripped off the electron. But the mass of the electron generally is much, much less than the mass of the atom or molecule. Okay, if you compare the mass of the electron to if you compare the mass of the electron to the mass of the proton is about 1,800 times heavier than the mass of the electron. Now, if you have a big molecule, the fact that you're missing the mass of the electron is not going to make a big difference. You're not going to have that kind of accuracy to notice that the electron mass is missing. Okay. And so this The mass spectrometer, and I have a nice figure of it in the PowerPoint notes. Looks like this. This is called the Bainbridge version of the mass spectrometer, where you can select different ions that have the same velocity with it. Whereas there's other versions. For example, one of the first person to develop an accurate spectrometer was a person named Aston. And Aston's was a little bit different. It had focusing elements in there, but it was able to choose a charge to mass ratio independent of the velocity of the particle. So it's a little bit different design. Okay. So you have to place, I mean, to measure the mass, you have to place the detector at the right location. Okay. Of course, you can change the magnetic field because you don't want to go around, and it's very difficult to move the detector. You can change the range of the particle by changing the magnetic field. That's what you do. You change B. You don't change the location of the detector to get the particle. You change B. Because all you got to do is turn a knob on the magnetic field, and then you'll get the particle to land on your detector. Okay. And then from the product of Q, B, and R, and knowing V, you can get the mass of the particle. Okay. And notice in this picture, the magnetic field points into the board, out of the board. Sorry. Another application is the cyclotron. The cyclotron was developed. Oops, that was too fast. The cyclotron was developed by Lawrence at Berkeley. Lawrence Berkeley National Lab. It's actually Lawrence and Livingston. And it was used to produce high energy particles for nuclear reactions. Nowadays, they're commercially made for the PET scan at hospitals. Some hospitals will actually have a cyclotron. And what they're used for is to produce radioactive isotopes of atoms, and they're short-lived. Yeah, these are interesting names. They're short-lived, like 2 minutes. What they do is they use this isotope, they put it in a sugar solution. It's actually glucose, a glucose solution, and they inject it in you right before they do the PET scan. And they scan your brain. And so what happens is the sugar solution, so if you have a part of your brain, a lot of times when you have some sort of illness, I don't know which illnesses they are, you have part of your brain that's more active than others. And so what they do is they inject this glucose solution in you that has the radioactive isotope. And the part of your brain that's more active will consume the glucose faster. And when that happens, then you have the radioactive material there. And as your brain is going to then be emitting radioactive particles. And so you have detectors all around you to take an image of your brain. These particles that are radioactive, they emit positrons. And you have positron detectors around to take an image. And so that's the PET scan. But you need you need a source of radioactive isotopes that are short-lived. They're really short-lived, like a couple minutes.
Is that the same idea of like an MRI?
The MRI is different because the MRI that uses the principle of nuclear magnetic resonance. They don't want to use the term nuclear magnetic resonance. And what they're doing is flipping the spin of the proton to take an image. And it's used, our chem department has an NMR device. And so it's a different kind of imaging technique. It is flipping the nuclear spin, but this one is actually injecting something radioactive in you. You're actually using a very high magnetic field in radio frequencies to flip the spin into the NMR or MRI. A little bit different. Just the magnetic fields are very high, so you can't go into a room with magnetic materials.
Yeah, you have to take off all your electronic stuff, right?
Yeah, because those are really strong fields. I mean, I have some strong magnets here, but those magnetic fields are quite strong. We're talking, several Tesla. Okay. So this is what a cyclotron looks like. Real quick, I'll talk about it. You have a particle that starts in the center of a circle, but this circle is different. You have the circles separated into two parts. They're called Ds because they have the shape of a D. And each D is at a different potential. So when the particle crosses from one D to the next, it gets accelerated. Remember that a magnetic field cannot change the velocity of the particles. Okay? A magnetic field cannot change the velocity of the particles. So what they had to do is they created two Ds that are separated and they're at different potentials. So every time a particle crosses the Ds, it gets accelerated. The frequency at which it accelerates, that it goes in a circle, is only dependent on the value of B. So you keep B constant, okay? And what happens is R gets bigger because it goes faster, okay? Because it goes faster, every time it crosses one of the Ds, because these are two different potentials, it accelerates. And so as V gets bigger, R gets bigger. So basically it spirals outward as it circles. Okay, this stays constant. Remember, omega, V is our omega. So we can we can solve this for omega. And omega is 2 pi times the frequency, so we can actually solve this for the frequency. One problem I got to tell you about, though, in this system is, let's say this is at, I'm going to make up numbers. Let's say this is at 1 volt and this is 0 volts. It's much higher than that. Okay? So let's say the particle crosses like this. It's a positively charged particle. It crosses here and accelerates, right? What happens when it gets to the other side and crosses?
Will it decelerate?
Yeah, so what you have to do is, the timing's got to be right, you actually have to flip the polarity of the Ds at the right rate. So it's got to be synchronized. Okay? So when it gets to this side, you have to flip the polarity. So knowing this, given the value of B, you have to know this. You have to know the frequency so that you can actually flip the polarity at the right time. Does that make sense? You have to flip the polarity of these Ds at the right time so that when this is at 1 volt and this is at 0 volt, it gets here and these flip around. So that every time it crosses, it accelerates. So that's another issue you got to deal with. Okay. But anyway, these are hospitals have them. The bigger hospitals tend to have these. Okay, not the small ones because they're expensive. Okay. So now what I want to do is talk about the force on a wire. We've talked about force on charge, but what about the force on a wire in a magnetic field? Can a magnetic field exert a force on a wire? Remember that a magnetic field will exert a force on a charge if it's moving and it has a component of its velocity perpendicular to the magnetic field. And it does no work on it. So I want to show you what happens when you put a wire in the magnetic field. I'm going to demonstrate it for you. This is going to happen very quick. And let me see if I can point things down here. Let me get rid of that slide. So I have a magnet here. Let me move some of this. I have so much stuff in the way here. If this class were in person, it'd be easy to show things. Okay, so I have a magnet here. Okay, can you all see the magnet? And there have a wire in the magnet. Yeah. Okay, this is actually a pretty strong magnet, okay? And so I have this power supply. By the way, this is the power supply you're probably going to be using to test your motors, because this thing does it says 40 amps, but you don't want to put 40 amps on your motor because you'll melt the wires. Okay, so let me plug this power supply in. And I'm going to run a large current very quickly through the wire. Okay, so it's white. Okay, and it's in the magnetic field. Here we go. Did you see the wire jump out?
Yeah.
Do it one more time. Of course, if I had the current going in the opposite direction, the wire would want to move down. So you can see a magnetic field can exert a significant force on a current carrying wire. And so what we're going to do is derive the equation. This is an equation we can derive. We can determine this experimentally, but I can derive it from our knowledge of the force on a charge in a magnetic field. So let me do that. Let me move my stuff back. Okay. So let's say we have a magnetic field that points into the board. And we have a wire carrying current to the right. The length of the wire is L. Okay? And the current is going to the right. We know there's going to be some sort of force on it because the velocity of the particles is perpendicular to the magnetic field. And I know that F is Q V cross B for a charged particle in magnetic field. But if I have a wire of this length in the magnetic field, I need to know how many charges are here at one time. I really need Q total. Okay, I really need Q total.
Professor?
Yeah.
For the equation, do you need the parentheses around the cross product or
Yeah,
no?
you do. Well, I should have it there. But I mean, it's not, whether I put it on this guy or this guy doesn't really matter. But
Okay,
But you're right. I mean, it's usually people write the parentheses. Thank you. But I need to know Q total. What is the total charge in here? Well, I need to know the volume of this wire and the number of charges per unit of volume. So the volume is just going to be the cross-sectional area of the wire times the length of the wire. Then if I multiply by the number of charges per unit volume, it gives me the total number of particles in here. And then I multiply by Q, the value of each of the charges, which is going to be the electrons. Then this is the total number, this is the total charge in that wire. Okay? So I'm going to write it like this. N times Q times A times L. And this V, though, is the drift velocity of the electrons in the wire. Well, let's leave it at that for now. What does the product of N, Q, A, and V sub D give you? Do you remember? Well, NQ times V sub D was the current density. This is the current density times the area. This is the current. So this is the current in the wire. Okay. So I can write this in terms of the current in the wire, and I'm going to define, instead of putting the vector here, since L is in the direction of the current, I'm going to write it in the following way. And so this is the equation for the force on a wire in a magnetic field. I times L cross B, where L is the vector that goes from this point to this point. And right now, its length is the length of this wire. Okay? Does that make sense? But the L is more general than that. I'm going to show you that in a minute. So that's the equation for the force on a wire in a magnetic field. And it obeys the right-hand rule. The only difference now is that you use the, instead of using V, use the direction of I in your right-hand rule. So this obeys the same right-hand rule as the force on a charged in a magnetic field. So what you do, point your fingers in the direction of I, curling towards the magnetic field. Your thumb points that way. Forces out of the board. So in this particular case, your thumb cannot point towards the magnetic field, okay, but it points upward. Okay. Or if you use these fingers, this is the direction of I, this is the direction of B, and then this is the direction of the force. Okay? You can do that too. Or of course, you can always do the cross product, which is the long way to do it. So on your exam, you're either going to be doing the right-hand rule or you're going to be evaluating cross products, which is evaluating the determinant. So the force on a wire in a magnetic field is this. Okay? And this assumes that the field is uniform. This equation assumes that, number one, the field is uniform, and the current density is uniform. If it is not uniform, then, and we're not going to do those problems here, then I can only calculate the force on an element of volume in the wire. If it's not uniform, then I'm going to write it like this. And this, I can only calculate over a unit of volume. So I would do the following. This is a volume, so I would write And this is the current density. And these delta F's, really, I got to make the volume small enough so I can, so this is constant. So I got to make this a dV, and this is a dF. And then I'd have to integrate over the volume. We're not going to do any of those problems, okay? Just so you're aware. So this is an equation assuming B is uniform. Okay? I'm going to make a couple more points and then we'll break for lunch. This also assumes that the angle between L and B stays constant. What if I have a magnetic field that points like this, and I have a wire that's not straight? I want to find the force on a wire between points A and B. I know that F is I, L, cross B. But if this direction constantly changes, if theta constantly changes, then what I have to do is break up my wire into small pieces. I got to find the force on this little ds. So I got to find the force on this little ds. I'm assuming the magnetic field's uniform for now, okay? Let's assume the magnetic field's uniform. And so this is going to be an easy integral. So this, if I integrate this, I is constant, B is constant. What does that integral in parentheses represent? The integral of ds is just a displacement. So this is just a displacement. And we define the vector L, because I did the case for the straight wire before. I defined the vector L as the vector that goes from A to B. It's the shortest distance between points A and point B. That's what L is. I mean, I did the straight wire. It's obvious in the case of a straight wire, but what if the wire is crooked? So that's a displacement. Okay? So L is a displacement. So this is going to be equal to I, L cross B. And L is the displacement of the current between points A and B. Now, what if I had a circular loop of wire in the magnetic field? If I integrate this over a closed path, what do I get? If I ended up where I started from, what's my displacement?
0.
0. So then the force on a wire, the force on a loop of wire in a uniform field is 0. I'll just write the word out. Remember, uniform. If the field is not uniform, that's not true. Okay? So that's something you need to remember.
That's a uniform magnetic field, right? Specifically, or
Yes, you're right. A uniform magnetic field. Well, what if the field is not uniform? Well, let me give you a quick example. and then we'll break for lunch. Suppose I have a bar magnet. Bar magnets produce non-uniform fields. And I have, the magnetic field kind of does this all the way around it. Okay, I just drew two of the field lines. And let me put a loop of wire in the magnetic field. I don't know if that's a good picture or not, but I don't know if you get the picture. I'm not an artist, sorry. This is a loop of wire carrying current I. So this is B. This magnetic field has a component that points up here and it points up here. We'll call it B sub Z. Well, I drew that loop bad. It should be horizontal. Okay, but the value of B sub Z is the same all the way around for that distance from the magnet. And so that component of the magnetic field is uniform all the way around the loop. It's not going to contribute to the force on that loop of wire. However, it has another component that points in the radial direction or away from the radial direction, away from the center of the circle. That thing changes direction all the way around. Its magnitude stays the same, but its direction changes all the way around. And this guy will contribute to the total force. And you can easily show that the force on it is going to be 2 pi r times I times B sub r, where B sub r is the radial component. You can actually show that. Okay? In fact, there's a problem in your book. So that's a good problem for you to try to do. And you can also show that the force is going to be perpendicular to both this and I, which will be in the z direction. Okay? So that's an example where you have a loop of wire in a non-uniform field, and the force on it will be non-zero. So after the break, I'm going to do two examples. One's numerical and one's not. And the numerical example that I'm going to be doing is designed to help you to do the next worksheet, the force on a wire in a non-uniform field. Okay? Oops. I didn't show you the slides, did I? Okay, I didn't show you these slides. Okay, so I'm going to do this example after lunch. So I'm going to take a break here, and we will meet 12:50 is okay?
Yeah.